Hi everybody, today I start medical chemistry for medicine for medical student. The first lecture is about chemistry. Chemistry is the study of the matter and change of its undergoes. What is the matter? Matter is anything that occupies space and the mass. Then we can say matter has a space, we can show volume, and it has a mass. We can say m is the mass. Then from the volume and the mass, we can calculate many important things like density. And the substance is the form of the matter that has a definite composition and distinct properties. It's very important. It's the form of the matter, we know the composition. Okay, we continue with classification of the matter. Matter can be classified for the type of separation, which can be separation by the physically or chemically. If we can separate physically, then the compound is the mixture, because only mixture we can separate physically. If we cannot separate physically, it is a pure substance. Now the mixture, how we can classify the mixture? Mixture, it is depend on the form and the situation, like composition uniform and or ununiform. If this composition is uniform, it's like solution. For example, sodium chloride in water. But if not, it is a heterogeneous mixture, like sand in water, stone in water. Okay. But pure substance, we cannot separate physically. We can separate chemically. If we can separate chemically, it is a compound. It is compounds is formed from the more than one element. Okay? And if we cannot chemically decompose or separation, it's an element, which we study in the periodic table. Element is a substance that we cannot separate into simple substance by chemical process. Element we can see in the periodic table. And also, it has a symbol. Okay, usually symbols can be one letter, the big letter, and two letter, which first one is the big and second one is small. For example, it's the one letter, big one letter, or helium. H is the big, E is the small. Bor is the B. Barium is the B is big, A is small. Carbon and calcium C is big, A is small. Usually we can have classify in the one letter elements or two letters. In the two letters, first is big, second is small. Compound is a substance composed of the atoms of two or more elements chemically, united in fixed in the proportions, and we can separate they are chemically. Compounds can be only separated into their pure compound by the chemical process or chemical means. Compounds has a formula. For example, water has H2O, ammonia NH3, glucose C6H12O6. All has a formula. The first theory about atom starts with the John Dalton's. John Dalton has four basic rules. The first for each element is made of the tiny particle called atom. It's very easy. Is the every substance, every element is made by the atom. The atoms of the given elements are identical. Okay, for which element we have the same atoms. The atoms of different elements are different in some fundamental way or ways. Chemical compounds are formed when different atoms combine with each other. It's very easy. For example, if we have a hydrogen element and oxygen element, we can produce H2O. And a given compound always has the same relative number, okay, and types of atom. And the lots of chemical reaction involved reorganization of the atom, change the way the bond, they change the bonds, and the atoms themselves are not changing the chemical reaction. From this Dalton experiment or Dalton theory, we can say we have to do some practice and or experiment, and in the end we understand that the atoms, we can find inside the atom two parts. Proton and neutron is inside the core or nucleus, and the electron is surrounded by the electron. The discovery of electron, we know because we know the electron is the negative charge, and its mass is very small, 1/10,000 times smaller than the mass of the proton. They use one palm powder model, which is use the cathode and anode. They use accelerated of the cathode ray from the in the magnetic way. As you see here in the magnetic way, we see the frozen screens go directly, but the electron go to the negative direction because it is a positive direction, because it is negative charge goes to the positive direction. Or we can use Rutherford methods. In the Rutherford methods, as you see here, there's a gold foil inside the detecting screen, and we have the alpha particle for the gold foil, and it's separate for several parts, and we can detect. As you see here, most of the particle passed right through. A few particles were deflected, and very few were gently deflected. And we say the nucleus is small, the nucleus is dense, and the nucleus is positively charged, which I mentioned, because inside the nucleus or core, we have a positive charge because it has a proton positive and neutron is a neutral, and the electron surround here. If you see the electron surround the proton and the neutron or nucleus. From the Rutherford model, we can see atoms has the two, as I mentioned, the nucleus positively charged and have a very small volume. The diameter is very low. It is a proton with a positive charge. Neutron is a neutral. And surrounded by a tiny negatively charged particle, which mass is very smaller than proton size or neutron size. From here we can expect what is what I mentioned property of the subatomic particle. Electron is the negative, proton is positive, neutron is neutral, and this two is in the nucleus. As you see, the mass, it is a 10 power minus 31, it's almost 10 power minus 4, 10,000 times the different or more. And the charge is exactly the same with the proton, negative, but the negative and the positive charge. We can find relative charge if you divide together, and we can find the ratio is the -1 and the +1. Okay? And neutron has a charge. And relative mass, if you see, Neutron and proton is almost relatively 1, but for the electron we couldn't find anything. Characteristic of atom. Atom has the atomic number of the proton in the nucleus. Usually in the neutral atom, which is not ions, the number of the proton is equal to the number of electron. Mass number, sum of the number of proton and the neutron, then we can say it A, usually we show with the R relative, it is a Z plus N. We can see also here. In the symbol, very is important when we have element symbol. In the left side, though lower, we can write atomic number, and in the left up, we write mass number. Okay, it is a neutral element. Then if we have a charge, we have to write charge here. Charge place. For example, for the sodium, the proton is 11, electron is the 11 because it's neutral, and the neutron is the 23 minus 11 is the 12. Isotope are the same element with a different neutron. If the different neutron, atomic mass also will be different. Okay, then isotope has a different A. Okay, A1, A2, okay, depend, okay? And usually A equal proton plus neutron 1, A2 is equal proton plus neutron 2, or we can find the third one or fourth one, and etc. Isotope is from the Greek word for same place, and most of the element has a mixture of isotope in the atmosphere or in the earth. The ratio of isotope is constant, okay? And usually we see the oxygen has the 3, for example, isotope. The first one, the normal oxygen, is the highest in percentage. They have all has the 8 proton and all has the 8 electron, but neutron is the normal oxygen is 8, and the other isotope is 9 and 10. For example, for hydrogen, we have a hydrogen. We say protium is the highest amount, and which has the 1 proton. Neutron is a 0 and 1 electron. But for the deuterium, which we can show by the D, is the lowest amount. In the high water is the D2O. The number of the neutron is also 1, proton also 1, electron also 1. But in the last one, tritium, which is radioactive, and we have a proton is again 1, electron is the 1, but neutron is the 2. It can produce beta emission, negative beta emission. Now we go to the radioactivity. Radioactivity is the spontaneous emission of radioactive by unstable nuclei. Okay? It's very easy how we can classify and how we can understand. We have 3 main types of the radioactive. It is alpha, beta, and gamma. What is the alpha? Alpha decay is the emitted particles helium to plus. It's very easy. And when we have a high proton and the proton number is more than 83, or atomic number is bigger than 83, in this case we can produce alpha. What's happened if the alpha particle production? Alpha particle production, it produce 1 helium size, okay? For example, I write one example. okay, for polonium. If you see here, for the alpha, polonium has a 239 and 94, and it changed to uranium is 235 and 92 plus helium, which is the 42. Then I can say element X with the N, with the excuse me, R and Z. If you see here, which I explain here, is the R always is on the top. In this case, convert to the Y element with the R minus 4, B and Z minus 2 plus alpha particle, which is around is the helium size. It's very easy, okay? I'm sorry, it's bad writing. It is a 239. Okay, 4 number decrease in the atomic mass and 2 number decrease in atomic number. But in the beta, we have 3 types: negative beta, positive beta, and also electron capture. The first one, we start with the negative beta. For example, I can write example the next page, or maybe it's better we open a page. For example, for negative beta, we have a carbon, it's 14. Carbon is 614. Produce beta negative plus, convert to the nitrogen, 14 and 7, plus antineutrino, plus electron. If you see here, this side, okay, excuse me, it is the electron or beta. As you see here, in the beta negative, we produce these 3, because electron, antineutrino, and as you see here, what is this one? It in the beta negative, atomic mass is a constant, but atomic number increased by 1. Okay, as you see here, what is the ratio in the negative? If the N to Z is too large, as you see here, N to Z is a big number. As you see the first example, N is the 8, Z is the 6, because why? Because 14 minus 6 is the 8, is the neutron number. Other example for the beta positive, as you see the beta positive, for example, carbon 10. If you see the carbon 10 with the 6, with the beta positive change to the boron 10 with the 5 plus neutrino and plus positron. Positron is the electron with positive charge. Okay? And as you see here, if we have a neutron to proton is the low number, because here we have a neutron. It is a 10 minus 6 is the 4, and the 4 to 6 it is the smaller. Okay. This was very good example for this and electron capture. We will study later in the X-ray, when again N to Z is too small. In the gamma decay, we usually have a not particle, it is a photon. The gamma photon is high energy. And if you see in the gamma decay, we can write many examples about the production of the photon in our, for example, in the chemistry, in the reaction. For example, if you see here, I write one example. Okay, for example, I write. Sometimes if I have to mention this, sometimes the gamma can becomes with other also alpha or beta. For example, radon 222.86 divide change to the again produce alpha, because alpha say decrease A with 4 and Z with 2, polonium plus alpha is the helium 4 2, and also produce gamma. Gamma is a high energy, some of them, because can produce gamma also is very important. Usually can in the process we can find gamma with also alpha or beta, and it is very important. We can say many other example, which for example in uranium we can also write other example. And it's excited form, and use the radioactive isotopes in research. For example, in the biochemical pharmacological investigation, and we can use a tritium and phosphorus 32 in industry. Also, we have our ecology. For example, for the ancient life, we can find the date of the method for the carbon half-life, 5,730 years. For example, if we have some mummy from the many years ago, we can find how many years ago he died. Half-life is very important. It's the time required to the quantity of the reduce to half of its initial volume. It's very important. Medical application of the radioactive isotope. We can use in the medical, we can use as a diagnosis and therapy. In the diagnosis, we usually use a low dose. And in therapy, we usually use a high dose if it's the same compound. For example, we can use iodine 131, which has a half-life 13 hours for thyroid gland for the diagnosis, but also we can use in the high amount for the therapy. In the CT or computed tomography, we use a gamma emission, or we have emission tomography, PET positron emission tomography for the fight the cancer cell, which we can use a carbon, nitrogen, or oxygen isotope or fluorine, which has a lower half-life. Or we can use SPECT, single photon emission computed tomography. Also, we can use it for the destroy the cancer cell. We use the cobalt-60 for the gamma emission for the destroy cancer cell. For cancer cell in the thyroid, we use our iodine 131. For example, PET positron emission tomography, I said it we use for the cancer cell. Usually we use one of these elements, okay? For example, F18. If we use the F18, we have to use in the part of the sugar, for example, glucose. Cancer cell has the highest capability to accept the glucose, and they need more glucose, and the metabolic rate is high. In this case, in the area which has cancer, unfortunately, they produce positron very easily with the positron, because positron is blind to the beta decay. And thank you very much for the pay attention for this lecture, and I hope I can explain next time the other lectures, and it will be useful, I hope, and have a good time, and see you in the next lecture.